Good morning, good afternoon, good evening, whatever the case may be, we are back in better than ever, and this is part 2 of Intersecting Planes. Let's get right back to it, shall we? Because we do not fear the Reaper, we do not fear intersecting planes, thanks to Blue Oyster Cult. We'll get back to them in just a second. So we left off right here. We had brilliantly solved this system, and we got 2, 4, -1. I did want to show you on your Inspire CX that you can solve it if you're on an exam that allows a calculator. Just by punching in or entering in the 3 equations using this particular app, I guess, or this part of the calculator. So you would just go to Menu, Algebra, oops, let me undo that, Menu, Algebra, and then Solve System of Linear Equations. Number of equations is 3, not 23, 3. It puts the variables in for you, and then you get LinSolve. And then you just enter in, just like I did here, x plus 3y minus z equals 15. The 3 different equations, hit enter, and the solution comes up. Also, I wanted to show you that you can, on our wonderful Inspire CX, graph planes, and you can see the rotation there. That's on auto rotate, and you can see the planes there. You can also manipulate it, blah, 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 blah. There's also a better view on the computer view if you have installed your software. Here's another rotation. But we're capable. It's just a little bit clunkier. That's why I use the online, because the online looked a little better. And also here you had to solve for z. Like, yeah, if you can see in the upper left-hand corner over here when I highlight, you can see that I had to solve for z in order to graph it. Anyway, onward we go. 2 more examples. I think we'll be able to get them done in this session. All right, so we have to solve the system here and interpret the result geometrically. So I made my matrix already ahead of time, but notice that I swapped the original row 1 and row 2. Why did I do that? Well, I saw that it's really, really beneficial if this is a 1 here. It just makes life easier. If row 1, column 1, it's a 1. And then the added bonus here is I had another 1 in the as the coefficient of the y. So I just swapped them, which is perfectly legal, because really there's no rhyme or reason as to the way that these are ordered. So I might as well reorder them to my convenience. I put the row operations here as to what I did, and I'll let you look at those. I'm just going to fill them in the interest of time. We would end up, if I take R2 minus 2R1, we would have 0, -3, 3, and 1. And for row 3, if I took row 3 minus 3 row 1, obviously to get this to be a 0, then I would have 0, -6, 6, and 2. Okay, so then I come up here. This one at row 2 is going to stay the same, 0, -3, 3, and 1. And I still need a 0 here, and wow, that's a horrible -6. So what I'm going to do is I'm going to take R3 minus 2 times R2, because that will make this a 0, and then I end up with 0, 0, 0, 0. That's interesting. Well, you have to ask yourself, is this possible? Is it possible for me to have values that make this particular equation true? And the answer is yes. 0 times anything is equal to 0 right here. The bad thing is if you had, let's say you had some constant like 7. There's no way this can be true. That is absurd. So if we have zeros here, we got to have a 0 here. Otherwise, we're not going to have any solutions. I just want to go back real quick and just show you, yeah, here. Where they say it's absurd. So you can go back here and review it if you want. Okay. Forward, forward, forward. Okay, so what do we do from here? Well, This is going to indicate that there are infinitely many solutions. So in order to get the nature of those solutions, we're going to let z equal t, okay? Because anything times t, 0 times anything is going to be 0. So we'll let z equal t. And so then that means in row 2, I would have negative 3y plus 3t is equal to 1. And solving for y, I would get negative 1/3 plus t. And then substituting all of that into row 1, in other words, z equals t, y equals negative 1/3 plus t, I would get x, or 1 times x, yeah, x plus negative 1/3 plus t, and then minus t, and that's going to equal 2. And without doing the algebra, I will tell you that we get x equal to 7/3. Okay, so the solutions to this system are going to have the form x equals 7/3, y equals negative 1/3 plus t, and z is equal to t. Okay, and t is an element of the real numbers, of course. Okay, so this covers infinitely number solutions, and this system represents 3 planes that intersect in a line, because I have parametric equations for each of these. This is the solution right here. Well, these are parametric equations, okay? What does it look like? Well, I graphed it on the online graphing system here. This is the original system, and you can see where they intersect into a line. Okay, let me reset the axis. I don't know if you can tell. No. Okay. So I'll just spin it around again. Of course, you can go to this website and investigate it further if you would like. But there we go. All right. One more example, and I did some of the matrices ahead of time again. Let's say I have this system here, and everything looks good except here. We're going to leave it as A, and where A takes all real values, because we're going to think a little bit. We're going to use row operations to reduce the system to echelon form. That's part A. And so again, I showed you what I'm going to do here, and I'm just going to fill it in the interest of time. This becomes 0, 5, 5, 15 by taking R2 minus 2R1. Again, the goal is to get this to be a 0. And then we get 0, 10, 10, and A plus 1. Okay, so I need a 0 here. So to do that, I'm going to take R3 minus 2 times R2. 10 minus 10 will give me the 0. So row 2 is going to stay the same, 0, 5, 5, 15. And then when I do this, I end up with 0, 0, 0, A minus 29. Okay? And so now we're going to go, so we've done part A, we're in echelon form, now we're going to do part B. So part B. When does the system have no solutions? When does it have no solutions? Well, it's going to have a no solutions when I have a 0 equal to a non-zero. Okay, when will that happen? Well, the only time this is 0 is when A is equal to 29, yes? So when A is not equal to 29, then we will have no solutions, because it's impossible, it's absurd, okay? And in this case, we would have 3 planes with no common point of intersection. We can't tell which case it is necessarily, but we would have 3, the minimum we would have to say is we have 3 planes with no common point or points of intersection, okay? And now, when does the system have infinitely many solutions? Find the solutions in this case and interpret them geometrically. Okay. Well, that's going to happen if A equals 29. Okay. That's the only possibility for us to have infinitely many solutions. And also, you know you're going to have infinitely many solutions when all these are 0. Okay. When your last row, when you get into echelon form and all these are 0, you'll have infinitely many solutions. So we're going to, again, let z equal t. Z is equal to t. And so then row 2 would be 5y plus 5t equals 15. And we would solve, and we would get y equals 3 minus t. Okay. And then in row 1, we would have 1 minus 2 times, we know that y is 3 minus t, 3 minus t, minus 1 times z, and z is t, so that's minus t, and that is going to be equal to negative 1. And so we would get x equals 5 minus t. Okay. So we have infinitely many solutions in the form x equals 5 minus t, y equals 3 minus t, and z equals t. Okay. In this case, we will have 3 planes which meet and align because we have 3 parametric equations. Okay. Well, that is all I have for this. Got it done in 2 videos. Very nice. Let's go back, check in with the Blue Oyster Cult, see how they're doing, and we will sign out to this awesome song. See if you can hear the cowbell. Is it coming? Here it comes. Not here. Here we go. Always need more cowbell. I am